is our project, Object Store Metadata Search. Now, OpenStack is a cloud computing platform, and Swift is one of the many tools that is offered by OpenStack. Now, what Swift is, it's an object storage system. You can interact with it using HTTP requests, and object storage is structured into counts, containers, and objects. Each object has its own associated metadata with it and contains attributes such as time created or deleted. Now, on the left, we have a Swift data model, and it shows the data hierarchy. And as you can see, the accounts hold containers, and containers hold the objects. On the right, we have the Swift architecture. As you can see, when the request comes in, it goes through what we call this proxy server pipeline. Now, this pipeline is made up of many modules that we call middleware, and each middleware has its own unique function. Now, when a request comes in, the first middleware takes the request, and in this case, it is the error catching middleware. Now, it processes the request and then sends it to the next middleware to process. And when the last module processes it, the result is then returned to the user. Now, Swift does not support much metadata functionality. As it stands, you can only query for metadata by accessing a single object. And the introduction of searchable metadata would allow users to access data by searching by searchable attributes. Now, and as a solution, our project was proposed. Now, last year, they implemented this metadata search functionality by implementing a database. The problem with this was their choice in database, which was SQLite, a non-scalable database, and the use of crawlers to populate that database. Now, crawlers are processes that are always running on the account, container, and object service. Now, as the data set stored in Swift grows larger, the inefficiency of the crawler becomes apparent because the time it takes for the crawler to scan the data and look for new metadata and objects increases linearly. Our project was to improve upon the scalability of this metadata database. And to do that, we would have to do several things. Research and integrate a scalable database. To implement and design a more efficient metadata collection system. And finish up any uncompleted API functionality.
Our approach was two-pronged. First off, we needed a scalable database for the metadata server backend. We needed a more efficient way to collect metadata for the server. On the database side, we needed an open source database with a good SQL interface for performing complex metadata queries, and a database that can scale to multi-million entry data sets. As there wasn't one database which fit all of our needs, we opted to select two databases and benchmark them later on to figure out which one is best for our needs. The two databases we went with were OrientDB and MariaDB. OrientDB is an open source, non-relational database which operates in a clustered configuration. And MariaDB is an open source fork of the MySQL project by the original founders of that project. We opted to run MariaDB with the Galera cluster and the MaxScale load balancer. This allows us to operate MariaDB in a multi-node clustered configuration featuring multi-master replication. And the MaxScale load balancer allows us to multiplex requests across each node in the server and have any data entered into one database replicated across all nodes in the cluster. Once we selected our database options, we needed to build a database abstraction layer on top of our metadata server, which allowed us to swap in or out any databases in the backend as we needed to. And this helped us benchmark to find the best solution. On the metadata collection side, we needed to replace the metadata crawlers with a more efficient and effective way of catching middleware, catching metadata, and using the Swift proxy pipeline. As you can see in this slide, we modified the Swift proxy server pipeline by adding a new metadata middleware and a new metadata server alongside the existing account, container, and object servers. This allows us to catch metadata off of objects as they come into the proxy server pipeline and insert them into the metadata server as it comes in. On the right, you'll see a UML diagram of our API spec, which lists each of the different HTTP requests and their various functions in the utility and backend.
The technologies we used for our project included OpenStack Swift as the foundation. Being that Swift is primarily written in Python, most of our code base is written in Python as well. The databases that we ultimately chose were OrangeDB and MariaDB, and we used Amazon Web Services for development and testing. Some of the challenges that we encountered were choosing the most suitable database option based on the API requirements, familiarizing ourselves with Swift, being that Swift is open source and ever changing. There's a severe lack of documentation resulting in the need to examine code to gain insight. And because of the lack of documentation, debugging is quite a challenge as well. And developing a scalable metadata collection procedure took some time as there are several approaches and we sought the most efficient. Finally, integrating a fully distributed version of OrientDB with our interface proved a challenge due to the maturity of the OrientDB project, including the lack of support, documentation, and information, and didn't ultimately come to fruition. However, our results with MariaDB proved quite favorable. As for accomplishments, getting our middleware interfacing correctly with our metadata server allowed us to catch requests as they enter Swift. We were able to explore different database options and attempted implementation of both candidates. We also implemented several features not included in the previous implementation, including extended query and attribute support, along with replication of the metadata database to provide redundancy in a similar fashion to Swift.
In order to gauge the performance of each database we implemented, we performed a series of benchmarks on each database. Our benchmarks consisted of writing and reading 150,000, 300,000, 600,000, and 1 million objects into and from each database. The databases we opted to benchmark were SQLite, trying to get a comparison with the previous project, and MariaDB in a 3-node configuration and MariaDB in a 5-node configuration. On the left here, you'll see the performance of write operations. You can see that SQLite performs quite poorly in comparison to MariaDB in both 3-node and 5-node configuration. You'll also notice that writes do not scale up with the added nodes in the MariaDB clusters. This is because writes are not intended to scale up in a multi-master replicated scenario. On the right, you'll see the performance of read operations. You'll notice that SQLite performs greater than MariaDB in a 3-node configuration, but is quickly surpassed by MariaDB in a 5-node configuration. I point out the fact that MariaDB's reads scale up with the number of nodes in the cluster. This is intended as writes are supposed to scale. I also bring your attention to the fact that there's no data for SQLite at the million scale of operations. This is because we weren't able to get data for the in-memory database at the scale of operations. Overall, our project had a few results. First off, just implementing the object storage metadata search API offers increased features previously unavailable to clients using OpenStack. Secondly, our metadata retrieval scheme demonstrates improved scalability by taking advantage of the proxy pipeline and replacing the SQLite backend. Thirdly, MariaDB scales reads with added nodes, outperforms SQLite on complex queries and insertions, and is able to store more records with decreased lengths. And that concludes our presentation. Any questions? Yep.
Yeah, so you scan for metadata as the data comes into the database. Do you have a way to process an archived, complete database that's already there?
Yeah, so I think that in that sort of situation, we have to use a sort of like hybrid crawler and proxy pipeline situation.
Swift itself doesn't exactly support you just kind of handing in something that already exists. You need to insert all the data. So because we're operating inside Swift, not as a separate